Hello everyone, welcome back to Exampreptool. So now in this particular video, we'll be talking about next important topic, which is Naive Bayes algorithm. If I talk about this particular algorithm, this has been asked consistently in previous years. And within this introductory kind of a lecture, we'll also be solving or we'll be building up a foundation for you to be able to solve that kind of a question as well. Okay, so let's get started. And apart from that, I hope you are enjoying these like important topic sessions with respect to the machine learning. That whichever are the like most prominent ones which are being asked regularly, or build up the foundation for entire ML subject. We are actually covering that. Cool. So as I talked about, let's get started with Naive Bayes. Before getting into the naive Bayes algorithm, we need to understand something like what exactly is a Bayes classifier, and then we'll be able to talk about what is naive Bayes classifier. Okay. And we'll see what is the problem with Bayes classifier and what problem naive Bayes classifier solves, how does it solve, and all that. So, as the name suggests, based classifier. So there are two things important. It's a classifier. That means I'm talking about supervised learning, in which we'll be classifying the class of a data point given. That what should be the class for that particular data point. Other thing being base. Now, the moment we get to the word of base, I hope it must be clear that we are going to talk about something related to the Bayes theorem, and that's what it actually uses. So Bayes classifier is a kind of a generative model or generative classifier we are having. We generally have two types of model over here when we talk about discriminative and generative. So it is actually a generative model. Simple reason, if we talk about it, actually talks about also able to learn that can we learn p of x, give x y together. Okay, if we can do that, we can always be able to sample the data as well. So all those generative models, if I talk about, these are those from which we do not really just solve the problem of classification, but we can sample the data as well if we get to know what was the true distribution from which any given data was actually generated. Now, I have said a lot, so let's just write certain things I talked about. So it's a generative model. Okay. So generative models are basically those where we actually learn this kind of a thing. If we can learn, in that case, that means if I know the distribution, for example, uniform distribution, binomial distribution, normal distribution, you can always sample some data from that. So it's like the generative models are built on this kind of an idea. If you can learn this, you can always sample new. So for an example, if you can learn the distribution of cat images, dog images, you can always generate new images, something like this. Okay. So that is the overall idea. Now, as I talked about generative model, so like for the Bayes classifier, what exactly is the idea, the way we actually classify? The idea is I should be able to tell what should be the p of y. Let's suppose the class I'm talking about is 1. So right now I'm considering binary class 0 1. So given your x is equal to, let's suppose this is the data point I have gotten, something like this. So I would like to find out, and in general, what we actually do in classifier is x is given to us. That means features are given. I would like to classify it as 1 or 0, or for a binary classifier problem. So I'd like to find this it out, whether it should be y equals 1 or 0. Now it's a probabilistic model. So let me add this thing as well. It's a probabilistic model. Now, the moment I talk about a probabilistic model, that means how would I relate it to the probability? So, if you remember logistic regression, SVM, and all that, we just say that if there is a line being crossed, a decision boundary being crossed, I would say it 1 or 0. So, we just directly say that. But from a probabilistic point of view, I would like to calculate that if x was this, what can be the probability that y will be 1? So it's like something like this. In our classification problem, the problem would behave like this. So I would be calculating both the things. What is the probability of y equals 1 given x is equal to something, something, versus what is probability of y equals 0? Because that is the other class we need to think about given our data. So whichever is higher value assigns its class. So that means if this probability is going to be higher, the class of this data point is going to be 1. If this probability is higher, in that case, I would say the class of the data point is going to be 0. So this is the basic idea for this kind of a thing. Now, why base? So I'll get to that. So if you know something like this, y is equal to something, x is equal to something, whenever I want to find it out, what this is a kind of a conditional probability. So and this being called as posterior. Okay, so how do I find that? So in term of other conditional probability, we generally calculate that. So it would be probability of x, whatever was given y is equal to whatever was required to be found, into probability of y is equal to, I'll fill it up, divide by what is the probability of x is equal to जो भी है, like whatever we are having over here. So this is the basic idea. Now if I would like to rewrite it to understand, let me just put it up. So something like this would be there. So let's suppose, as I mentioned, so it's going to be like, what is the data point I'm talking about? X1, X2, X3. And let's suppose I'm talking about a category A. Okay. And there are only two classes, A comma B. Okay. So what is this value into this? It divide by this. So this is a usual Bayes theorem I'm talking about. X1, comma X2, comma X3. Okay. And what is the probability of seeing this data overall? So it's like if I just talk about what these individually are called. So like over here, I said this is posterior. This term is called likelihood. This term is called prior. That means what is the prior knowledge about this class I'm having? Like in general, if you tell me that how many percentage of the people belong to this class in general, even if you do not consider the data. So if you have some subjective bias in your mind, so that is this prior. This is called evidence. So like given like what is the data, what would be the probability that y the class would be A? This is the posterior we need to calculate. So for that we need likelihood that for category A, what is the probability that I would get to see such kind of a data, which is called likelihood. Prior evidence means like this conditional probability, a posterior we were actually calculating. So out of that, how many evidences of this thing existing exist? So what is the probability of x taking this value? This is called evidence. Now, the way we generally break it in Bayes theorem is, I'll just write that expression as well so that it's clear, and then we'll get to the point of what is the problem with this Bayes classifier and how Naive Bayes would be solving that problem. So I'll just write the blanks as it is. I would not fill it up right now because we already have that clarity. Only for the denominator, I would like to fill it up. Divide by. Now this P of X can be, broken down the way we actually calculate the total probability. Something like this. Summation P of X is equal to given Y is equal to into probability of Y is equal to. Like for an example, if this is binary classifier, so we have two classes. So to get this, I would like to see what is the probability of getting this when the category is, let's suppose, B, and then we will multiply it by the prior of B plus what is the probability of seeing this when the category is A over here, and then prior for A. And this is the same data point we were having over here. So like in general, the way we actually would like to write it up is, like I would like to write this as this one only. So if it was A, this data point itself, over here, let's suppose I'm saying the class, and what do I mean by that is class belongs to A comma B. One time I'll calculate this for A, one time I'll calculate for B, and then I will add it up. So this is the idea, the way we generally use by Bayes theorem. Okay, so this entire idea is clear. Now, to form the basis of Naive Bayes, you first of all should have to look at what is the problem with the way we need to calculate this one. If I can calculate this easily, in that case, we are already towards the end that, okay, we'll be able to find out what is the probability. And if I can tell the probability, I can always tell what is going to be the class of this particular data point. And that would be easier, not a big issue. Now, the problem, let's avoid the problem, but the other thing which I can use is, so you can see, if I want to find out the probability for A, the posterior for A, I'll get A over here, and it would be this, which can be broken down in this term. So that means once over here, we'll get A, then B. If I want to find out it for B, I'll get B over here, and this is same. So that means if I just break it up, I'll get the entire one time A, one time B. So can you see, to calculate this posterior, the denominator remains same for both the calculation, be it when I want to calculate for y is equal to A, or be it for y is equal to B. So denominator remains same. So that means in that way, I can reduce my computation. I would not focus upon calculating this. I can always just focus on this, because this is a constant. So it's something like this. And I just wanted to calculate two numbers. Let's suppose P and Q. And like in both the cases, like P was something like, for an example, let's suppose K by A, and Q was something like L by A. The point is, I just want to say, I just want to find out whether P is greater than Q or Q is greater than P. Depending upon that, I will say what is the class. So if you just look at inside, should I even care about calculating A? The answer, this doesn't really make sense if I just want to compare these, which one is greater. So in that case, I can just compare K and L and then assign. No need to calculate the denominator part and then assign the class. So that means one computational problem is being solved. I would not really be calculating this. It would reduce some overhead. I would just calculate that. Point to be noted, this will not give me the probability. This will now not be the probability, because it is just product of these two. If I divide by this, then it becomes the probability, but this is not the probability. So it's something like I'm just finding a product of two, value for whichever is higher. I know probability would also be higher for that, because ultimately I need to divide by the same number for both. So just avoid that. Just find out the product for whichever the product value is higher. I would say the class is for that particular category only. I hope this idea is clear. Now, this particular thing is clear. So I'll just talk in terms of this now, only this one. Okay. So if I just talk about with respect to this thing only, so I'll start again. So let's suppose the data looks like this. So I have x1, not, or let me just say x1 for this, x2, x3, and then I'm having y. So x1, x2, x3 are the features, okay? And let's suppose I'm having like some good number of data points, n, and this is d features I'm having, okay? So these are the feature name, and the moment I will be referring to the values of these feature, I would like x1, x2, and x3. I will write it like this. The value of the features, capital X1, capital X2, capital X3, I would like to write like this. So if I want to find out what is the probability, like, because I need to find out the category of a class or the class label, I would be doing something like this: 0 1 0 0 0 1. Let's suppose something like this is there, and then we will be having some values which we'll talk about. So let's suppose I would like to find out this. Given x is equal to, let's suppose, because x means a particular data point I'm talking about. That means what is the value of my x1, x2, x3? That means I'm saying x1, comma x2, comma x3. This would be written as probability of x being equal to x1, comma x2, comma x3, given y is equal to 0 into probability of y is equal to 0. Now this I can write further as, this one as that my x1 is equal to small x1, comma x2 is equal to small x2, comma x3 is equal to small x3, given y is equal to 0 into probability of y equals 0. This is the final calculation I'm getting over here. Okay, this means same, because x means this vector means I'm saying that overall the feature values are x1, x2, x3. Now this is a little problematic. So why it's a problematic situation is, to be able to find out the joint distribution itself is a problem. Okay, so joint distribution generally have this it's really difficult to calculate the joint distribution, and you understand that. But if somehow you convert it into a way such that you just care about what is x is equal to x1 when the category was y is equal to 0, and the situation when x2 is only x2, a capital X2 is equal to small x2 for the category y is equal to 0, that would be much better case, rather than saying when all this x1, x2, x3 would be a particular set of values, then for a category what exactly is that probability. So joint distribution is a little difficult to calculate and identify. Okay, and I can compare the number of parameters as well very soon. So what actually happens is, this is actually difficult to calculate. So this is my simple Bayes classifier based approach. In Naive Bayes classifier, what we do is we convert it into a case of x1 given y is equal to 0, probability of x2 is equal to x2 given y equals 0, probability of x3 equals x3 given y is equal to 0, and then whatever was the prior. So this has been converted to this. That means what is happening over here? How do I convert my Bayes classifier to the Naive Bayes one? By assumption of conditional independence. What is the assumption? That conditionally all the features are independent. Conditional independence. This is the assumption. Now, conditional independence would say that, okay, x1, x2, x3, what are the values they are taking, conditioned on y equals 0. I can write them independently, because on y equals 0 they are conditionally independent. So I can just write them separately, and now this would be much easier to calculate for me. This would be much easier to calculate for me. This would be much easier for me to calculate. So one, joint distribution is itself a overhead. Like, how do we find it out? The number of parameters would also be much higher. So I'll just show you like how the number of parameter reduces, and that actually forms the basis of your one of the standard question being asked in GATE DA exam as well for ML. I'll talk about that. So let's suppose I'll bring both of these scenarios. Like I'm writing it y equals 0, y equals 1 deliberately, though I know there will be just one column for y. Either it would be y is equal to 0 or y is equal to 1. The way I'm writing is you'll get to see why am I writing this. So I'm saying, for an example, let's assume that all assumption features as well as target variable y are binary variables. That means they can take only two values, 0 1, a b c d, a b or c d, 3 4, maybe something like this, true false, success failure, high low, okay, something like this. So all are binary variables. So if I'm saying, and this is simply a Bayes classifier based approach I'll be talking about. Over here I'll be talking about Naive Bayes classifier based approach. So in that case, I hope you understand this particular point over here, that I need to calculate everything like this. X1 is equal to this, X2 is equal to this, X3 is equal to this, given Y is equal to this. I need to have this value of probability. I need to get this probability value, joint distribution. Now that means I need to have, like, how many probability values would I need to determine this? In case of just binary variable I'm just talking about, and then if it changes to, let's suppose, multinomial variable, it changes a lot. Okay, so if it's a binary variable, what would be happening in that case? This can take two values, this can take two values, this can take two values. Overall, their combination, total combination of x1, x2, x3 is equal to 8 combination they can create. Okay, now I need to know, because I would be needing these probabilities. For that, what I would need, combination of these 8 given a particular y value, what is the probability? That means how many combination I can have over here? 8 given this y. I should be having this particular value of p. What is this p value? Now for each of those different combination, I should have the values. That means if I just show something like this, let's suppose like all were 0 1 0 1 kind of a thing. So what is the probability of x is equal to, if I just write 0 0 0 given y equals, let's suppose, 0, what is the probability of x is equal to 0 0 1 given y is equal to 0? What is the probability of x is equal to 0 1 0 given y is equal to 0? What is the probability of x is equal to 0 1 1? What is the probability, and so on? So there are 8 combinations. So I would be needing total 8 probability values for a category, for one category. Now for both the category, how many I need? Because how many classes do I have? I have 2 classes, y is equal to 0, y equals 1. So for both, I have to multiply. So it would be 8 into 2, 16. Now, these are just the, for likelihood, this is how many I need for likelihood only. Now there is a prior term as well which I need. So you can see this, I got to know how many such probability values would be required, because I can get any x. So in that case, I should know the probability for all those x's given y equals particular category. After that, I need to multiply it with my prior as well. That means for, like, if I have 2 classes, I need to have p equals y, sorry, p of y equals 0. I need to know p of y equals 0 and p of y equals 1 as well. Both are required for likelihood. So I hope you can see the total number of parameters. That means 2 more parameters or probability values are required, because if I have these, then only I'll be able to calculate my posterior values. 2 more parameters. So all in all, how many I got? 16 plus 18. So sorry, 16 plus 2, 18. This is the total number of parameters I would require in this case. How 16? We had, like, if I say all these three were like binary variables, so 2 for each possibility, 2 into 22, 8 combinations are possible entirely. Now, what is the probability of those 8 combination for a particular class? So how many classes do I have? 2 classes. So 2 into whatever number of combination, 2 into 8, 16 likelihood values I should have. Plus, how many prior are required? The number of classes. That means 2, 16 plus 2, 18. So I hope this idea is clear. Now, if I go by the same idea over here in Naive Bayes classifier, what I am saying is I would not really be needing a combination of all because they are independent. So what matters to me is what is P of x1 is equal to 0 given y equals 0, and what is P of x1 is equal to 1 given y is equal to 0. Similarly, what is the probability of x2 being equal to 0 given y equals 0? What is the probability of x2 being equal to uh, 1 given y equals 0. Similarly, probability of x3 being equal to 0, y given 0. Probability of x3 being equal to 1 given y equals 0. So how many likelihood values, like, to get this value? To get this, now because of conditional independence, this has been broken down to this. So how many these probability values are required? 2 only would be there. How many? 2 only. How many? 2 only. And see, I know there is a multiplication, but we are not multiplying 2 into 22. Overall, how many probability values do I need? So you can see for each class this time, I would need 6 only. 6 probability values or parameters for each class. Now, if I want to find out for 2 classes, it would be 6 into 2 for each class, plus we need a prior. So prior would remain same in both the cases. There are 2 prior values, 6 into 2, 12, 12 plus 2, 14 parameters. So I hope you can see how much it has decreased. Now, if I just increase it, let's suppose instead of just 3, let's suppose x was d-dimensional. X had like d-dimensional features, or d number of, or let me say, sorry, if I say we had f number of binary features, and let's suppose I'm talking about c number of classes. So what would happen in Bayes classifier and what would happen in Naive Bayes classifier? Let's just write it up if you could have understood this. So because there are f number of binary features, each one is binary, I know. So that means there is a possibility of 2 values for each feature. 2 into 2 into 2, how many times? How many features we have? F. So there would be 2 to the power f combination of feature values. Combination of feature values. Now, what about the likelihood values, the probability values I would need? I would need for all the combination per category. So that means how many categories or class there are? So there is C. So that means 2 to the power F into C plus the prior values. C. It would be 2 to the power F plus 1 into C. You can see over here. Now, the moment I change it to Naive Bayes classifier, what would change now? So you can see the moment I change it, the simple change would be I would not need all those combination. For each of f features, each one is binary. So I'll just need 2 probability values for each. So 2 for first plus 2 for second plus 2 for other one. How many times? F times. Because y equals, let's suppose f1 was the first feature, f1 is equal to 0 or f1 is equal to 1, f2 is equal to 0 or f2 is equal to 1. So like there are 2 possibilities, so 2 probabilities for both, and how many features we have? F. So 2f per category would be required. How many classes do I have? C plus C number of priors. It would become, now you can see, C into 2f plus 1. So you can see it is a little exponential over here, and it is simple, what should I say, a linear over here, like 2 into f, and this is 2 to the power f. How does the number of parameters reduces? The computational power also decreases over here, making it a little faster. Okay, so if this is clear, I hope we just understood the total number of parameters. But in real and like when you would be needing it, you do not really talk about total parameters. You talk about the minimum possible parameters. Now there is a thing. So I hope you know, if I talk about minimum parameters, it would change. Why would it change? I'll give you the example. If I tell you that I have 5 probability values, okay, like, yeah, 5 probability values which sum to 1. So how many values do I actually need? Or at any point of time, how many values would I always be needing if I want to use it? So the idea is, I know like overall sum is always going to be 1 for the probabilities. So the last variable P5 can always be determined in terms of the other one, 1 minus sigma of Pi I going from 1 to 4. I hope you're getting this idea what I'm saying over here, because the same idea will be using to minimize the number of parameters for each of those cases. So what I'm saying is, if you know there are 5 events which are if combined they are independent events also, if I'm just talking about that, in that case the sum of their probability is going to be 1 if they are exhaustive events. Okay, exhaustive, mutually exclusive, something like all those conditions are satisfied. You do not really need all the 5 variables at any given point, at any point of time. You would just need 4. The fifth one can be always be determined using 1 minus the sum of other 4. So this is the idea. Now if I talk about how would it reduce or how would it be used over here, I'll tell you. So let's just talk about for simple Bayes classifier first, and then I'll talk about how we will be using it for Naive Bayes. For Bayes classifier, minimum parameters. So as I talked about, let's take an example of 3 columns only, features. Okay, again binary. So what would happen is, given a class, I know the sum of all the 8, because how many total combination possible for x1, x2, x3 is actually 8, which we have seen already. Now, do I need all the 8 probabilities always? No. Why? Because I know for a given category, the sum of all the possible values of x1, x2, x3 combined, it would sum up to give 1. So that means what I'm saying is, just giving you example, not the summation. If I just write it like this, P of x is equal to 0, 0, 0, given y is equal to 0, plus probability of x is equal to 0, 0, 1, given y is equal to 0, dot, dot, dot. Last में what we will be getting, probability of x is equal to 1, 1, 1, given y is equal to 0. I know this would be 1. So do I need overall 8 parameters over here? Can you see this? You would just need 7 parameters. You just need any 7 values. If you know that, you can always calculate the rest. So that means for any category or class, you need 7 probabilities, not 8. Now that means 7 into 2 overall for likelihood. Okay. Now for the prior, how many do we actually need? So if it's a P of y is equal to 1 and P of y is equal to 0, again same thing. I know this can be written in terms of this 1 minus p of y equals 1, because I know p of y equals 0 plus p of y equals 1 is equal to 1. So again, I would not need two probability values over here. Okay, like all in all, if I talk about, I know there are like two parameters over here, 8 parameters over there, but the minimum number of parameters, if I talk about that, I would not really need all 8. I would not really need really two over here. I just need one over here to represent both. If I know this, I can determine this. If I know this, I can determine this. So the total number of parameters would reduce to 7 into 2 for the likelihood plus one value for the prior. It would become 15 over here. I hope you can see. Okay. For the same case, from 18 to 15 we are getting, if I'm talking about minimum number of parameters. Now on a similar line, in Naive Bayes, what would happen? So now we have already broken it down to like x given y, x1 given y, x2 given y, and all those were binary only. So what would happen? X1 is equal to any, like if I'm saying 1, let me just remove this. The same principle would apply over here. 0 plus probability of x1 equals 0 given y is equal to 0 is also 1. I know that. So that means I would just need 1 over here, not 2. So that means one probability is required, one parameter minimum is required for each feature given a class. How many features we had? We had 3 features. So I would just multiply it by 3. So in all, like 3 are the number of minimum parameters which are required for a class to determine the likelihood. So 3 into class, this one, 3 into, sorry, this was for features, my bad, as there were 3 features. So all in all, I'm getting 3 into number of classes I'm having, because for each class I want all those. So that is 2. So that means 6 parameters would be required for likelihood, plus 1 for prior. That means it would be all in all 7 parameters ultimately I'm getting. Okay, so I'll just write it up once again. So in short, same problem, 3 binary features. If I just bring it up, total parameter and minimum parameter, I'll write now parameter and minimum parameters meter. So over here, what was the answer? I hope you remember this was 18 and this was 16. Over here, we just calculated it. We were getting it around 14 and we are getting it 7. So I hope you can see the minimum parameters would be much lesser. Okay. 7 and yeah, we calculated all these now. Yeah, 14 and 18 was there. Yes, so I hope I have written, yeah, it was 14, my bad. Oh, for minimum Bayes class. Yeah, we were getting this only. Uh, 6 into 2, yeah, it was 14. It was 14. So you can see over here, my bad. That if I talk about minimum parameters, it reduces from 18 to 14 and it reduces from 14 to 7. Now I'll give you just general question and we'll give you the answer for that. And that would be the end of our Bayes classifier discussion, because that had helped us in understanding how does Bayes classifier actually work, how do we calculate the posterior, and if we get to know the posterior, we can actually determine what is going to be the class, because higher the posterior, higher would be the chances of that particular class. Okay, so let me just take one more. So x1, x2, x3, and let's suppose x4. These are the four. And let's suppose I'm having C classes, and this can take, let's suppose A, oh no, PQRS. Yeah, that would be better. I'm just bringing it up just for the use case based problem. Let's suppose this can take P number of values, this can take Q number of values, this can take R number of values, this can take S number of values. What is the total parameters? Total and minimum parameters for Bayes classifier, the same total parameters and minimum parameters for Naive Bayes classifier. If I want to find out what would be those values. So I'm saying I have four features. X1 can take P values, X2 can take Q values, X3 can take R values, X4 can take S values. If I talk about that, what would be the total and minimum parameters for both the cases, Bayes classifier, Naive Bayes classifier, and there are C classes. So the way we will go is, if I talk about total parameters for both the cases. So let me just write total and minimum. Okay, I'll write like this. So what is the total combination of x1, x2, x3, x4? It would be P into Q into R into S. That is the possible combination. Per class, that many combination. And I need those many likelihood values. So that means for each of the class, I would be needing PQRS, P into Q into R into S number of parameters. So for C classes, how many would it be? P into Q into R into S into C would be all those. And plus for the prior, what would be the number of parameters? C classes, so C probability values would be required. So it would be simply C into PQRS plus 1. I hope you can see why. C into PQRS, because PQRS has the total number of like combination possible per class. So I need all those probabilities. How many categories or classes? C. So C into PQRS plus C number of priors would be required. So all in all, this one. What would change over here for NBC, Naive Bayes classifier? So per class, I need P, I need Q, I need R, I need S. So that means, and how many prior? C. So it would be C times of P plus Q plus R plus S plus 1. Because for for X1 I need just P, for this one I just need Q, for this one I need just R, for this one I just need S. P plus Q plus R plus C. Per class would be just P plus Q plus R plus C. For C classes, it would be C into P plus Q plus R plus S. Now C number of priors would be there, so all this. Minimum, if I talk about what would change, so the change would be that for each class, I would need one less than overall. So PQRS minus 1 would be the overall number of likelihood values which would be required per class. Now for C class, it would be C into PQRS minus 1. Now how many priors would be required? C minus 1. So if I just would like to write it the way we wrote it over here as well, PQRS minus 1 for, because I would not really need for the last combination. And this is per class. So for C classes, it would be C into this one. Plus how many priors are required? C minus 1 priors are required. Now what would happen over here? Same thing. So I would need P minus 1 probability, Q minus 1 probability, R minus 1, S minus 1 per class. So it would be P plus Q plus R plus S minus 4. Because I was subtracting 1 for each of these, because for this one, for just a single class right now I'm talking about, I need P minus 1 combination, P minus 1 values, Q minus 1 values, R minus 1 values, S minus 1 values. So all in all, what is the sum? P plus Q plus R plus S minus 4 per class. Plus how many priors? C minus 1. I hope I'm clear. This way you can generalize it to any way if you want to take it up. This is the total number of parameters which we will be requiring to basically estimate what we need. I hope I'm clear. This was overall idea of Bayes classifier. So this way, so this is one of the way, the number of parameters. The other type of question being asked is what is going to be the posterior value, or what is going to be the likelihood values. Those might come. Now, how do we calculate that is always given from the question perspective, but there is a space. There are some special cases where uh, for calculating the posterior, like we write, no, if I want to determine just class, I know how to, but sometimes they actually want us to calculate this posterior. So this would be the thing in denominator. Now, what can happen because of this is, if that particular kind of data does not really exist, what would be happening in that case? Okay, one problem over here. Okay, the other thing is, if over here you can see we were multiplying all these. Okay, so what if this combination does not exist? That means that second feature never had a value like x2 for this category. This would become 0 in that case. If it was not there, the entire posterior value would become 0. Do we want that? Just because of one missing part, I cannot make the entire probability to be 0, saying that the probability of this class would be 0. No, we can't really do that. So there we do some smoothing to adjust for those cases where the probability can be 0. Okay, and the way we do is actually the Laplace smoothing is one of the way we do it. The other way, like there are a number of ways to do the smoothing, but that is one of the way. And then we calculate all those. So this was just a hint, just a given hint that how do we evaluate all those probabilities, which has been covered in the paid course over here. Okay, but I hope with respect to this introductory lecture on Naive Bayes classifier over here itself, you are able to learn that how does Naive Bayes classifier actually work, how are the number of parameters being determined, because this is the question, standard question I have seen in like in the sample paper, in the actual exam as well, I guess it was there. So yeah, it's pretty much important for you to understand how do we calculate the number of parameters. You should know that idea. Minimum and total both must be clear. Okay, apart from that, yeah, so there are a number of things can't be covered over here because this is just the introductory and kind of a crash course kind of for this particular algorithm. You need to learn about how are the decision boundaries. Would the decision boundaries be linear or it would be non-linear? Is there something there is something related like LDA as well? How is it related to Naive Bayes classifier? How is it related to Bayes classifier? All that stuff has been covered in the paid course. Okay, so that was all guys from my side on the Naive Bayes classifier. I hope you understood. I hope you enjoyed this particular lecture. See you guys in the next one, which would be the last lecture with respect to the important concepts in machine learning, which would be your decision trees, because the concepts I am covering, you will get to see definitely a question from these in your main GATE DA exam. Okay, I hope you're enjoying. You can share it with your friends. Thank you guys for watching out this lecture. Bye.